Greetings and welcome to lecture number 19 on the course Introduction to Fourier Analysis. On the previous lecture we defined a few basic operations on the space of tempered distributions, each of which preserved the space of tempered distributions. Tempered distributions could be differentiated, multiplied by polynomials and Schwarz functions, and perhaps most importantly, the Fourier transform of a tempered distribution could be defined as another tempered distribution. The definition was simple. Lambda hat evaluated at phi equals lambda evaluated at hat phi for all Schwarz functions phi. We also saw that if the tempered distribution lambda is induced by an LP function f with p between 1 and 2, then the distributional Fourier transform hat lambda of f agrees with the tempered distribution induced by the LQ function hat f. In other words, the Fourier transform of tempered distributions extends the Fourier transform of LP functions. But the range of the distributional definition is far from limited to LP spaces. As the final result of the previous lecture, we showed that the Fourier transform defines an invertible map on the space of tempered distributions, and there is even a concrete inversion formula. Lambda is the Fourier transform of tilde hat lambda. We begin this lecture with another simple but useful result, Theorem 4.17, which extends the familiar formula from the space of Schwarz functions to the space of tempered distributions. Let lambda be a tempered distribution and let alpha be a multi-index. Then, as we saw on the previous lecture, d alpha of lambda can be defined as a tempered distribution. We will revise the definition in a moment during the proof. Theorem 4.17 states that the Fourier transform of this tempered distribution agrees with the tempered distribution which is obtained by multiplying hat lambda with the monomial 2 pi ix to the power alpha. The proof of Theorem 4.17 is entirely based on the fact that a similar formula holds for Schwarz functions, although one has to pay a little attention. To be accurate, we will need the dual or the converse formula for Schwarz functions, which was also recorded in proposition 3.8. This formula stated that if alpha is a multi-index, then the alpha derivative of the Fourier transform of phi equals the Fourier transform of the function phi multiplied by the monomial minus 2 pi ix to the power alpha. Further, by the linearity of the Fourier transform, any multiplicative constants can be pulled out of this expression. For reasons to become apparent shortly, we choose to pull out only all of the powers of the constant minus 1. After this, you can check that the right-hand side equals minus 1 to the power order of alpha times the Fourier transform of the function phi times 2 pi ix to the power alpha. With this formula in hand, the proof of Theorem 4.17 is straightforward. We fix a Schwarz function phi and start with the definition. The Fourier transform of the distribution d alpha of lambda evaluated at phi equals the distribution d alpha of lambda evaluated at hat phi. Next, as we advertised, we recall the definition of the distribution d alpha of lambda. Its action on a Schwarz function, this time hat phi, is defined by minus 1 to the power order of alpha times lambda evaluated at d alpha of hat phi. To proceed from here, we apply the formula for Schwarz functions we discussed just above. The alpha derivative of hat phi equals the Fourier transform of the function phi times 2 pi ix to the power alpha, multiplied by the constant minus 1 to the power order of alpha. Next, we use the linearity of the tempered distribution lambda to move the factor minus 1 to the power order of alpha inside the distribution, where it cancels out with the same constant. So we are left with lambda evaluated at the Fourier transform of phi times 2 pi ix to the power alpha. From this point on, we just apply the definitions. First, the previous expression equals the Fourier transform of lambda evaluated at phi times 2 pi ix to the power alpha. Finally, this expression equals, again by definition, the value of the distribution 2 pi ix to the power alpha times the Fourier transform of lambda evaluated at phi. As we now compare the left and right hand sides of the long chain of equations, we find that the Fourier transform of d alpha of lambda equals 2 pi ix to the power alpha times the Fourier transform of lambda. This is what we claimed, so the proof of theorem 4.17 is complete. At this point, you can probably believe that also the dual formula holds. Namely, if alpha is a multi-index, then the Fourier transform of minus 2 pi ix to the power alpha times lambda equals d alpha of hat lambda. The proof of this formula is completely analogous to the previous argument, and we leave it as an exercise. In the next example, example 4.18, we used this formula to calculate the Fourier transforms of polynomials. Recall that any polynomial f, or more generally, a polynomially bounded function f, induces a tempered distribution lambda subscript f by the familiar formula lambda subscript f at phi equals the integral of f times phi. So the Fourier transform of polynomials is well defined as the tempered distribution hat lambda subscript f. In example 4.18, we will find a more concrete expression for this object. The starting point is proposition 4.14, where we already calculated one special case of this example, namely the Fourier transform of the function 1 equals the Dirac measure. Or, if you prefer to be painfully precise, the distributional Fourier transform of the tempered distribution lambda subscript 1 equals the tempered distribution lambda subscript delta 0 induced by the Dirac measure. The plan is now to combine this fact with the formula we just mentioned above concerning the Fourier transforms of tempered distributions multiplied by monomials. In order to avoid notational complications, we concentrate on a simple special case, namely computing the Fourier transform of the polynomial p of x equals x, and only for x on the real line. Once you get this idea, the generalization to other polynomials and higher dimensions is entirely straightforward. We start by writing the polynomial p of x in the following way. P of x equals I over 2 pi times minus 2 pi ix times 1. Since the left and the right hand sides are the same functions, also the tempered distributions induced by these functions are the same. The tempered distribution induced by p equals I over 2 pi times the tempered distribution induced by 1 times the monomial minus 2 pi ix. Now we can compute the Fourier transform of the polynomial p, which by definition means the Fourier transform of the tempered distribution induced by p. We apply the formula we just derived to see that this Fourier transform equals I over 2 pi times the Fourier transform of the distribution minus 2 pi ix times lambda subscript 1. Here we may recognize an expression which appeared in the formula star we mentioned above, in the special case where the multi-index alpha is just the number 1. We apply the formula star to find that this expression equals the first derivative of the Fourier transform of lambda subscript 1. Finally, we use the information that the Fourier transform of lambda subscript 1 equals the tempered distribution induced by the Dirac measure. After this rather formal computation, we have arrived at the formula which says that the distributional Fourier transform of the polynomial p of x is x equals I over 2 pi times the first derivative of the distribution lambda subscript delta 0. This may appear hopelessly abstract, but it really is not. We just need to break down a few layers of definitions. First of all, what does the first derivative of the distribution lambda subscript delta 0 really mean? If we hit the Schwarz function phi with this distribution, we first find, by definition, minus 1 times the distribution lambda subscript delta 0 acting on the first derivative of phi. Next, again by definition, this expression equals minus 1 times the integral of the derivative of phi with respect to the Dirac measure. Recall that we are working on the real line, so d phi is just the usual first derivative of phi, namely phi prime. Finally, by definition of the Dirac measure, this integral equals the value of phi prime at the origin. Now we can rewrite the formula hat p equals I over 2 pi times d lambda subscript delta 0 in a much more concrete way. And this formula means precisely that if phi is any Schwarz function on the real line, then the integral of hat phi of x times x dx, which is the Fourier transform of p evaluated at phi by definition, equals minus I over 2 pi times phi prime evaluated at 0. The equality between the left and right hand sides of this formula may not be the most useful formula in the world, but at least it's a concrete and non-trivial equation concerning all Schwarz functions. As we already mentioned, a similar formula holds for more general polynomials and in all dimensions, with essentially the same argument. As a voluntary exercise, you can check that if p is a general polynomial on Rd, then the Fourier transform of p evaluated at the Schwarz function phi equals a certain linear combination of the alpha derivatives of phi evaluated at the origin. The coefficients C alpha in this formula are easily determined from the coefficients of the polynomial p. If, for example, p of x is x, then the sum here only contains one term, and the coefficient C alpha is equal to minus I over pi, as we just demonstrated above. We then turn to the last topic on these lecture notes, which concerns one more operation on the space of tempered distributions, namely convolution. As we have just seen, tempered distributions can be differentiated and multiplied by either Schwarz functions or polynomials, and the result is still a tempered distribution. But one basic operation is missing from this list: convolution. Can tempered distributions be convolved? This might sound like an incredibly dry and academic question when you first hear it, but this impression just couldn't be further from the truth. The fact that Fourier transform turns convolutions into products is one of the most useful properties of the Fourier transform in real applications. We have seen that this formula is true for Schwarz functions in proposition 3.8, and now we would like to extend it to tempered distributions if possible. The first step in this process is to figure out what convolution even means in the setting of distributions. We will motivate and eventually give the definition on this lecture, but theorems will have to wait until the next lectures. Recall how the convolution of two Schwarz functions, or more generally two L1 functions, f and g, was defined. The convolution of f and g at x equals the integral of f at y times g at x minus y dy. The convolution of two L1 functions f and g defines another L1 function whose Fourier transform was computed in proposition 3.8. Its value at xi equals the product of the Fourier transforms of f and g at xi for all vectors xi in Rd. Concerning tempered distributions, we will in fact not be able to define the convolution of two tempered distributions. We have to make do with something a little bit less ambitious, namely defining the convolution between a tempered distribution lambda and a Schwarz function phi. It turns out that this can be done in such a way that the convolution is still a tempered distribution and its Fourier transform satisfies the familiar product formula. The Fourier transform of lambda convolved with phi equals the product of hat phi with the Fourier transform of lambda. From this formula, one can get an indication why it is so difficult to define the convolution of two general tempered distributions. If this was possible, then the Fourier transform of the convolution should equal the product of the Fourier transforms of these two tempered distributions. However, we have not defined what the product of two tempered distributions means, and as far as I know, this is not even possible, at least not in a satisfactory way. For this reason, we focus on defining the convolution between a tempered distribution and a Schwarz function. To motivate the definition, let's write the convolution between two Schwarz functions, psi and phi, in a slightly strange way. Namely, the convolution at x equals first the integral of psi at y times phi at x minus y dy, and this integral can be written as the tempered distribution lambda subscript psi evaluated at the Schwarz function tau x of tilde phi. The notation here needs some clarification. First of all, the object lambda subscript psi is just the usual tempered distribution induced by psi. Second, the notation tilde phi means the same as always, namely tilde phi at y equals phi at minus y. Finally, the notation tau x is probably a new notation. If phi is a function on Rd and x is a vector in Rd, the notation tau x phi refers to the function on Rd defined by tau x phi at y equals phi at y minus x for all y in Rd. With this notation, it will probably take you a few moments to verify that the convolution of psi and phi at x really equals the distribution lambda subscript psi evaluated at the function tau x of tilde phi. I suggest pausing the video now and clarifying this for yourself before we continue. Now we are ready to define the convolution between a tempered distribution lambda and a Schwarz function phi. Note that the usual integral formula for convolution, namely integral of lambda at y times phi at x minus y dy, would make no sense if lambda is not the function. However, the final expression we saw above makes perfect sense. Lambda evaluated at the Schwarz function tau x of tilde phi. Indeed, tau x of tilde phi is just another Schwarz function, and we can hit it with the distribution lambda. We take this formula as the definition of convolution, definition 4.19. If lambda is a tempered distribution and phi is a Schwarz function, then the convolution between lambda and phi is defined to be the function whose value at the vector x in Rd is given by the value of lambda evaluated at the Schwarz function tau x of tilde phi. We have now defined the convolution of lambda and phi, but we don't know very much about it. It is evidently a function of some sort, but what can we say about this function? In particular, is it so regular that it can be used to define a tempered distribution? Fortunately, the answer is positive, but this requires a surprisingly non-trivial argument. We will see this on the next lecture. This concludes lecture number 19 on the course Introduction to Fourier Analysis. Goodbye for now.